Okay, just somebody coming in. Okay, so hello and welcome to our session this morning, our first session of the last day of the CELDA conference. I hope you enjoyed the conference so far. We have this session titled Assessment of Exploratory Technologies. I think we have all full papers in here, so this will be 25 minutes for presentation and 5 minutes for discussion for each of the papers. And let's get right into it and get started using adaptive mastery testing in assessment management systems. I think Muitin Sain will present that work, which sounds very familiar to me. So Muitin, the screen is yours, please.
Okay, thank you. Good morning to everyone. I'm sharing my screen now. Here. Yes. Can you see my screen?
Yes.
Okay, thank you. First of all, welcome to our session. Good morning again. I am Muitin Sain. I am a postdoc researcher at University of Mannheim. We are working with Professor Fentaler actually, and also I am a senior expert at the Presidency of Turkey in Human Resource Office actually. But this work is not about this. We have large groups for this work, and we have the part of a project actually, and our project was financially supported by the Scientific and Technological Research Council of Turkey. And our title, as you mentioned before, using adaptive mastery testing in assessment management systems. I would like to give some information about assessment. After that, I will introduce our systems and just some basic results, initial preliminary results of our system. Oops. Yes, here. When we look at the e-learning environments work in favor of autonomous learners, and actually we can say that the assessment is the heart of the learning process actually, and individual online learning environments and assessment environments and designs that recognize and guide the learner enable them to learn at an individual pace come to the fore, especially during the COVID-19 process, unfortunately, all over the world, and e-learning environments where students can test themselves and make a judgment about themselves contribute to the assessment process. I would like to inform you about, I would like to give some information about adaptive mastery testing, but before that, when we look at the systems, the key feature of adaptive test is that each respondent is tested based on their ability. Adaptive test application require a large item pool of computed parameters actually, and variable length mastery tests maximize the possibility of making correct classification decision as well as shorten the test length. When we look at the literature, we can see two different adaptive tests. One of them, the adaptive mastery testings, we can determine the learners if they master or non-master about in a subject, or we can determine the learners ability level about the subjects. But if we determine the learners ability level, we should conduct computer adaptive testing, but we need more and more items for the computer adaptive testings. The limitation of us, we didn't have a large item pool. Then we conducted the adaptive mastery testings, and this method is a method in which item selection methods from variable length mastery test and test termination rules are applied adaptively in this test actually. Master testing is performed to decide whether an individual is master or non-master according to the test results observed in a subject. And there are two hypotheses for this test. Learner is master or learner is non-master actually, and we can use some different algorithm for this test. the sequential probability ratio test, the SPRT algorithm, has been administered to determine the master or non-masters of students. And item examined incompatibility is employed as the item selection algorithms. This process takes place until it's decided to examine is master or non-master. The SPRT rule introduced by Volt is widely used for IRT-based adaptive computer testing, actually. When this test is utilized, it's possible to reach more consistent and optimal results just with fewer questions. Then we used this test. What's our aim? In this study, the adaptive master testing in assessment management system was designed and developed actually. Throughout these systems, students can test themselves, recognize their strengths and weaknesses, and determine their learning subject-based competencies, actually. And we developed the software, actually, and for this reason, we used rapid prototyping software development process. And this process consists of 4 steps: need analysis, prototype development as design, and prototype development research, and implementation of the system and evaluation of the system, actually. And our participants, we have 98 participants, actually. These students are graduate and undergraduate students from the State University of Turkey. And when we look at their gender, the 65% of our participants are female, and the 35% of our participants are male students. And actually, this module is our just one part of our project, actually, because this is just one part, adaptive master testing module in our systems, and we use this system. We use this module in order to pre-test and assessment of learning. We are trying to determine learners' performance before access to the systems, and after that, yes, we are trying to determine learners are master or non-master in each subject. And if the learners are master, yes, they can shift to next subject in the system, actually. Just I want to see what's the module and all. And when we look at our systems, there are some different modules. For example, in the systems, in our testing environment, learner interface, presentation model, and presentation model connecting with assessment model and also domain model. And we have an item pool here, and also learners can interact with the system with a learner interface. And also in the learner interface, this is our learner interface. You can see the subject in this side. These are the subjects. Also, we used this test for statistics course in Turkey. And also you can see the questions. You can see the items here. These are quiz items, and these are options. And then the next question. And also, we presented to the learners some performance dashboard, actually. For example, learners can see their performance according to the master testing. For example, the total number of the responding, or total number of the correct and responding about the learners. And this is also learners can compare themselves with their peers for each subject, actually, here. And the learner model, when we look at our learner model, data is stored about the users. We stored usernames, user passwords, user codes, and information about the individual characters of the users of the participants, actually. When we look at the assessment model, SPRT can produce more efficient results than CAT with fewer items. If we have fewer items, if our item pool is not large, yes, we can use SPRT for the efficient results. SPRT uses the information which points located above or below the threshold score determine the classification status actually. And also SPRT was used as a termination rule. And as I said before, there are two hypotheses for SPRT, null hypothesis and alternative hypothesis, and presented below. H0 hypothesis is below of the threshold, and the other is below of the threshold, and null hypothesis is non-master. The other hypothesis is master. As you can see here ability level, cut point, and indifference region. And when we look at our domain model focused on the learning objective, which are the smallest part of the learning process, and the competency of the learner's master or non-master is revealed for these learning objectives. If our aim is classify the learners, we can use the adaptive master testing actually. And when we look at the domain model, in the domain model, course, unit, topic, and subject are stored by the domain model in the system. And we collected data from the participants, from 98 participants actually, and our data, our parameters or our metrics are the number of take tests by students, number of correct answers, incorrect answers, total number of attempt to response, and also we produce just two more metrics according to these metrics actually. I want to give some information about these metrics and about these results. When we look at the results, we have, we have, as you know, 98 participants and a number of different learning objectives in the systems. We presented to learners just 4 subjects, and all learners take the exam. For example, we can see that our minimum score is 1. It means that yes, all learners interact with the systems and at least take just 1 test. But when we look at the master learning objectives, some students are non-master for some subject. And also taking tests, yes, minimum the minimum value is 1 and 12. When we look at the correct answer, the maximum is 86. The minimum is. Some learners interact, log into the systems, and maybe they didn't respond any correct response. All didn't respond any questions. When we look at the incorrect answer, yes, the minimum value is 0 and the maximum value is 70, and you can see the average and the standard deviation actually. And also you can see the number of total response of the learners, minimum, maximum, average, and the standard deviation scores. These are the descriptive information about the log data. How can we, sorry. And also, we produced a score from these metrics. We produced a subject ratio score. This score, the learning objective divided subject ratio was obtained. Was obtained by dividing the number of master learning objective by the total number of learning objective. If this ratio is high, it means that the student is so successful on the basis of learning objective. According to the results, I will see the results actually with a graphic. The 37 of the students in the system are masters in all learning objectives, and also 27 of learners in 3 learning. They are masters in 3 subjects, and it means the 75 of the learners are master. And also the 13 of the learners are master in 2 learning subjects, and also the 13 of the students are non-master in any of the subjects actually. And here you can see the graphics. As you can see, these are this means yes, the master students. The 50% of the learners are approximately the 37% of the learners are the master. It means the master students, and the master students in 3 subjects, 2 subjects, 1 subject, and these are the non-master students for non-master students of all subjects, actually, it means. And also we have the other score attempt ratio. This ratio calculates the attempt ratio. The number of learning objective is divided by the number of the tests, and then this value obtained was subtract from 1. If the value is increasing, it means that students take tests many times in the same learning objective. When we look at the results, actually, the 52 of the students were determined as a masters by the system for the first time. And also, we can see the system, we can see these results. Actually, half of the students take the exam just once. After that, they are master in this subject. And these are our results. When we look at our conclusion, the competencies of students can be monitored and students' learning awareness can be increased through mastery testing during the learning process, provided that learning management systems and assessment management systems using the same learning model are integrated. And also, master testing environment was developed in order to determine the students' master or non-master status according to the subject within the scope of this research. It can be expressed that most of the students interacted with most of the achievements submitted to themselves, and also the fact that more than half of the students were determined as the master in the first test they received for each achievement is another finding we obtained. And also the master testing system developed as the part of the research is limited to the sequential probability ratio testing algorithm. And also it's possible to use more advanced algorithms such as expert and expert 1 using the item parameters, or maybe computer adaptive testing. If we have a large item pool, also we can use the computer adaptive testing. Another limitation of the study is the usage of log data only in order to evaluate the systems. And in the next stage, it's projected to perform an analysis in terms of system usability and student satisfaction, actually. And that's all. The end of my presentation. Thank you for listening.
Thank you very much, Mutin, for this presentation. I think we learned a lot about the idea of having adaptive testing in our digital space and learning environments. So is there any questions from the audience or comments you would like to ask? Then please use the chat or also come up and open your mic.
Yeah, hello, I have a question. Based on the design of the prototype, did you follow a linear process, or did you do an iterative process changing between the design and the definition and testing of the prototype? And also, if you did a co-design process with teachers and students based on the usability of the tool?
Actually, we didn't use the regular process because, as you know, the software development process are iterative process. Mm-hmm. Yes, there are some shifted from the design and evaluation, and this system or this screenshot of the systems was the first phase of the system, actually. After that, yes, we developed our new generation of the systems, but yes, it was an iterative process, actually. Yeah. And for the second question, it's about participants.
Yeah, no, well, if you counted with students or teachers, with the final users, in order to design the prototype.
Yeah. We are using the learners' opinions in order to design and in order to improve our systems. But the usable test, we haven't conducted the usable test right now, but yes, in the next stage, we will do it.
Thank you.
You're welcome. Thank you.
Other questions or comments?
Yeah. please.
So Martin, could you a little bit elaborate on the algorithm you've been using and maybe the expert algorithm? Where do you see the differences or the advantages if you use the SPRT algorithm versus the expert algorithm? Is there what would be your next stage or recommendation for others to implement?
Actually, when we look at these algorithms, for example, when we look at in the literature, we used SPRT algorithms in this study, but in the next stage or in our other project, also the Bayesian network approach can use, or the Bayesian knowledge tracing approach can use. Or if we have a larger item pool, we have more and more items, also computer adaptive testings can use, but it was our limitation. In addition to this, when we look at that, the SPRT algorithm can use for two different aims, actually. For example, we can use SPRT algorithm in order to determine learners' competency, master or non-master, or we can use the SPRT algorithm as a terminating rule in the systems. Yes, in the systems we use SPRT algorithm, but in the next stage in our feature research, we want to use knowledge Bayesian tracing or knowledge or Bayesian network, actually. Or yes, we have a lot of items. If we have item parameters, we would like to use computer adaptive testing.
Yeah, I think that's very reasonable to move forward with different algorithms and also maybe test, the different algorithms and the different findings coming out of the different algorithms. So that would be an interesting contribution. Maybe a last question, if there's nothing coming from the audience so far. Any questions in the audience? Not so far. Okay, so I was thinking about the idea of mastery and non-mastery classifications. Yeah. So if a researcher is coming now or a teacher saying, well, I do want to have more classifications than master and non-master. So maybe having 4 tiers. So the non-master, the not so much master, the more advanced master, and the master, kind of four then 2 classifications. What do you think? Would that be reasonable to implement as well?
Yes, absolutely. This opinion is reasonable because when we look at the literature, it expressed that if we want to classify learners 2 or more categories, you can use this approach. Yeah, it's definitely reasonable.
Yeah, maybe that would be also interesting to see how learners react towards different, classifications. So if there's a 2-tier classification versus a 4-tier classification, and is there a difference in terms of the perception of the learners and the satisfaction with the tool, etc., and of course also their learning progress. So that might be all interesting aspects to include in future research as well. Yeah. Okay, any other questions coming out of the audience? Seems not to be the case. So thank you very much again, Martin, for your insightful work. And I think we are congratulating you on the work and welcoming you back for future research to CELDA, of course. So let's move into our next presentation, and that is computational techniques for data science applied to broaden the knowledge between citizen science and education. I think Miriam is already in the room. So please, the screen is yours.
Thank you. So I'm going to share my screen. I think you can see it. Perfect. Well, good morning, everyone. And I'm going to present our work, computational techniques for data science applied to broaden the knowledge between citizen science and education. And these are the contents of my presentation. I will start with a brief introduction. Then I will talk about the research context and the methodology. I will show the results obtained from this research, and then I will finish with the conclusion and the future work. Science and technology has become part of our everyday life. We use computers, we use mobile phones, the cars, the public transport, while the news update us on the latest COVID situation. These are trending topics which require scientific literacy in order to understand the problem and find a solution. And despite this, the future generation are demotivated and uninterested when it comes to science and technology studies. The formal education settings are the spaces where the learning takes place, but it can happen without an educator. The teachers have the knowledge and skills, the methodology, resources, and materials used in the classroom, along with an innovative curriculum, can guarantee this learning and motivation. In this regard, citizen science can play an important role. And in improving scientific literacy, the knowledge about science and technology, and the development of the required skills. Also, the use of materials, the communication with other scientists, with other volunteers, and reading scientific documentation developed by the project can improve communication skills and also the vocabulary of the participants. For this reason, the objective of the paper is to show the potential that the web scraping and data mining techniques offer in order to better understand the practice of citizen science, and also how this metadata about citizen science project can be used for educational purposes. This preliminary study will also contribute to bringing citizen science closer to the education sector, the education spaces, and equipping educators with new tools and new data to support the educational process. So for those who doesn't know the citizen science, although there are many definitions for citizen science for the purpose of this research, we will define citizen science as the active engagement of general public in scientific research tasks. The participation in citizen science is done in projects in which volunteers, scientists, educators, technologists, and evaluators work together. The task developed by the participants and the duration of this task depends on the definition of the project and also the research needs. The citizen scientists, also called volunteers, do a range of activities such as monitoring species, or collecting data and analyzing data, for instance. And the participation or the development of this task can be online, can be face-to-face, or both, a combination. And also it's important that citizen science projects develop materials, protocols, training courses, or workshops in order to support the volunteers during the participation. And also the communication between the scientist and the participant, it's very important to obtaining good results at the end of the research. Citizen science can also enhance public understanding of science and also contribute to STEAM career motivation. Citizen science can also promote values such as ecology or the respect of the natural environment. Or for instance, citizen science resources, tools, and information about, for example, the citizen science projects can be integrated into a classroom to inspire teachers during the learning design activities, and also can have an impact on student scientific literacy, knowledge, and motivation toward science. Although the aspects between the citizen science practice and educational context have been analyzed, this connection is still not always clear. In fact, there are citizen science projects related to education and few projects which define the learning outcomes of the research. For citizen science, it's common to share information about the citizen science project, such as description or the materials used on different online platforms. To collect this information, web scraping methods and data mining techniques have been explored during this research. But the problem is that this platform don't follow metadata standards. So data mining techniques have been used to extract the conclusion from the text and can be also very useful for obtaining conclusion from the data extracted from citizen science projects from these online platforms. Apart from the data analysis, it's important to visualize the results obtained to validate the hypothesis, to get insights for the data, and also as a communication tool for the end users. Dashboards, for instance, are excellent tools to integrate all the data and facilitate the visualization of this data and conclusions obtained from the text. Also, technology-based tools such as dashboards have been developed historically to help teachers in their educational practice. So it's not new in an educational context to integrate these kind of tools. The purpose of this research is to understand the connection between citizen science and education, and also identify the information of the data that can support the educational process. Data analysis algorithms have been applied in many scientific fields, but there is a lack, or we found that there is a lack of knowledge of how to apply these computational analytic techniques to better understand the gap between citizen science and the connection with education. For this research, metadata or information about citizen science projects and resources from 377 citizen science projects have been extracted from 3 key citizen science platforms: the European platform, the European Citizen Science Platform, the Observatorio de la Ciencia Ciudadana from Spain, and the Oficina de la Ciencia Ciudadana from Barcelona. The following graph, the graph in this slide, shows the steps followed to extract, analyze, and show the conclusions or visualize the conclusions in a tool. First, the first step is we selected the 3 platforms mentioned in the previous slide because of the data interest and also the region that it covers. You can see that one is European, the other is from Spain, and the last one is from Barcelona, a city, different regional levels. The secondary, in order to follow the robots exclusion protocol, for each website, for each online platform, we selected the robots.txt file, which includes the data extraction restriction. It's very important. For this preliminary study, we developed a scraper or a robot to automate the manual work of extracting the data from the websites. So we developed a crawler using Python technology with Selenium web scraping software. And we use this crawler to extract the data, the information from citizen science projects, from the Spanish platform and also the Barcelona platform. But for the European platform, we use their own application programming interface or API because they have one. So it was very useful to extract this data. Once the data had been collected, it was stored in different files, platform by platform, with information classified by type of data. Once we have this data stored, before analyzing the data, we had to pre-process it by applying different methodologies such as cleaning or data cleaning, tokenization, or lemmatization. It's commonly used for text mining techniques. Finally, once the data was pre-processed, we analyzed the data. For example, we counted the number of occurrences of a certain word by applying the inverse document frequency technique. Or we also identify the people's name or institutions between the text automatically by applying the name entity recognition technique. Once we had analyzed all the information, we integrated all this information and combined it in various dashboards created with a Tableau tool. It's a common tool, very used for many companies. I'm going to present now the results obtained after the analysis of the data. All the data and the outcomes have been integrated into different dashboards, as I said, using Tableau on a single website. So the final result is a website with all these dashboards. The following slides show a screenshot of the graphs and the dashboards developed. So in this dashboard, you can see now in this slide, you can see a comparative analysis of the data from the 3 different platforms. We extracted 377 projects, 188 from the Spanish platform, 176 from the European platform, and 13 from the Barcelona platform. The problem is that as many platforms have information from the same citizen science project, in the database we had 16 duplicated projects. This project came from the European platform and the Spanish platform when the data was extracted. So we eliminated the duplicators, or we combined the data from these duplicated projects. The 2 temporal graphs in the previous dashboard, the same you can see on the right, show the start and end date of the project. That's information that sometimes platform informs, not always, but it's common to have this kind of information. And as can be seen during the last 10 years, there has been a growing interest in citizen science. It's important to know how up to date the data and the materials are, because the more recent the start date, the more innovative the project will be. And it could also help teachers to know which projects are ongoing in case they want to participate in a project. Regarding the educational aspects, because this is a tool for educators, in order to classify the projects that contain educational aspects, keywords related to education, such as schools or education or classroom, have been identified. As we want to apply automatic methods, we had to define this list of keywords in order to automatically classify the description of the projects. Another information or a piece of information extracted was the topic of the citizen science project. Each platform contains a topic information which indicates the discipline of the project. So as each platform has its own internal classification, we decided to group all these disciplines into 4 main categories, which are applied science, life science, social science, and physical science. We did one analysis based on the European Citizen Science Platform, the most common project related to biodiversity, ecology and environment, and also education. Those are the projects classified, or the most important category in this platform, or the category which contains more projects, is this biodiversity, ecology and environment. And the results obtained from the classification of the data into these 4 categories after applying this algorithm of classification was the discipline life science, which is directly connected to biodiversity, ecology and environment category from the European platform. And considering the educational perspective, we could say that the topics addressed by citizen science projects are similar to the ones in the curriculum, especially for the secondary education curriculum. As has been mentioned previously, by participating in citizen science projects, the participants can improve communication skills and also vocabulary. This is important because our hypothesis is that by not only participating in citizen science, but also exploring terminology, the students can develop these skills and science literacy and also the vocabulary. For this reason, this tool integrates terminology used by each project, and the educators can explore this vocabulary and identify words related to the subject, and citizen science projects which cover the terms they are interested. The figure on the left shows a list of words extracted from each project from the European platform, and the figure on the right shows a word cloud with the most used words by the projects on the European platform. So it's like a combination of the left figure. It's also common for volunteers in citizen science to use technology. So the type of technology they use depends on how the project was designed and the task developed by participants. As I said, they can, for example, monitoring species, and they can also use an application to store the data when they monitoring the species. So in general, the most common tools used in ICT are the ICT devices, such as smartphones or cameras. This information is interesting for the educators because the use of ICT tools in education settings could improve scientific literacy. And by knowing the technology used by citizen science projects, the educators could, for instance, design learning activities based on the use of a tool and integrate this tool into the class. And the last dashboard we developed was this one, which shows the materials extracted from the European and the Spanish platform. Only from these two, because the Barcelona platform doesn't contain these materials. So 212 resources such as books, datasets, guidelines, scientific publications were extracted from these platforms. As the resources may or may not be directly related to citizen science, this information have been classified into two groups. And the educators could explore these materials and resources and use them in an educational context. So we have now the possibility of integrate ICT tools, for instance, or also the materials or resources developed by the projects. To sum up, the analysis carried out in this paper shows the potential for analyzing large amount of data related to citizen science in order to better understand the citizen science practice and, in particular, how this data can be used for the educational purposes, or how educators can use this data for educational purposes. The main limitations are the inconsistencies in the data structure of each citizen science platform, and also the different languages used by the platform, because we selected 3 platforms with 3 different languages. When the data is integrated into a single database or a single repository, such as these files I explained, both limitations make the analysis very, very difficult. That's why we apply the data mining techniques, and others have to be explored in order to solve the problem of the languages. The lessons learned from this proof of concept are the access to the citizen science project information can help teachers to design learning activities. And beside that, the students that explore the information could find many examples of different citizen science projects or scientific projects, motivating or stimulating them to learn more about science. Also having an overview of citizen science vocabulary or scientific vocabulary in combination with specific teaching strategies can support better vocabulary development and can affect literacy. The teachers' access to scientific validated resources can support them during the learning design process. And also identifying technology can help teachers decide which tool can be used in the classroom. Finally, thinking of the future work, and also it's a limitation for this research, as the educators have not been involved in this study, it's planned to organize co-design workshop with them to better understand the needs and also to design the final tool where we will integrate the data. There are many citizen science platforms in Europe. Now we extracted the data from 3 key citizen science platforms. So we want to extract the data from more online platforms which contain information about citizen science. It could be citizen science platforms and also other platforms which contains information about citizen science. Thank you for your attention. And also I want to mention the CELDA projects because we've been working on that, and part of the work is, or the work done for this research is also part of the CELDA project. And thank you.
Miriam, for your presentation. I think this is a very interesting project, diving deep into data available and reusing the data, which can be or having lots of educational benefits out of the data you extracted. So are there any questions coming from the audience for Miriam on this presentation? Just give you a minute, maybe also use the chat or open up your microphone. So when we are talking about dashboard design, I think it's always important to think about the competence the users might have in using dashboards and understanding what dashboards are representing. So I think you mentioned in one of your last slides that you want to build co-design workshops with teachers or even students. So how would you set up these workshops? Do you have already some plans in mind how these workshops would look like?
Yeah, we are planning it. So now we are designing a workshop that combines both parts, the part of the data and also the part of the functionalities of the tool. Because for us, it's very important to understand which data could help the teachers, but also it's important to see how teachers use the tools and what are their needs. For instance, we thought that maybe it's possible to integrate information from open repositories, because maybe it helps teachers during their learning design process. So yeah, the first part, based on the data exploration, I think we will share with them some examples of the kind of data we have, because now we did the part of the extracting information from more online citizen science projects. So we have more information to share with them. So we will them different examples and they will select the data they think it's relevant or it's important or they need. And the second part, it's something we need to think about, but it will be a combination of how integrate this data and also what functionalities they will need based on the tools they've been using, because we don't want to create something new. We want to integrate all the tools they have in order to help them during the educational process.
Yeah, I think that's very very important. What you mentioned here, that it's not building new things, but yeah, using what is available, because we have so many data available in this space. And also, I think it should be very easy to handle for the teachers. If it's getting too complicated, teachers won't use it. So that's always my experience with dashboards. Providing too many options and being too overwhelming for, you know, getting quick results, because teachers in most times don't have much time to, you know, prepare and move forward, because they want to quickly come to a solution and in their design processes. So it's I think it should be very quickly coming to a result. I think that's an important issue, but that will show your design approach surely as well. Another thing was and looking at the usability of the platform. What methodology are you using? Would you use just interviews, or would you use like observations, or would you use even eye tracking or data collection within the systems, or how did you envision that, or didn't you move forward that far yet?
You mean by testing the prototype once it's developed? Yeah, good question, because I didn't think about that. But in the research group where I'm working, it's the type group from UPF, they have experience on that. They develop a tool, the CELDA Plus, and I think they use questionnaires and also eye tracking for some of the tests they did with the prototyping, but I don't know which one I will use. But if you can recommend me someone.
I think a combination of different methodologies might really be, you know, providing you different insights, and so that might be helpful to have observations and have maybe retrospective interviews, but also maybe using eye track at some specific elements as well. So you see where the main use points are, and what things are highlighted on the platform or not. So that might be a good combination of different methodologies, I believe.
Yes. Something I think it's important also is to see how the teachers work with the tool in the environment where they will be working, not in our office because it's not useful. And also something I want to say is that it's focused for secondary teachers or science secondary teachers, not primary, because I'm a teacher in a secondary school, so I think it could be easily to find teachers based on this educational level.
Yeah, wonderful. Yeah, I think that's a good level of approaching teachers in the secondary levels, and they might find lots of useful information based on your project. So, any other questions out of the audience for Miriam for this wonderful project?
If you don't mind, I want to share the CS Track project website.
Yeah, sure. Yes.
So
yes,
in
please.
case,
we have a few minutes left.
Yeah, in case someone is interested in what we are doing, and also in citizen science, because it's not a common practice in science, but it's very interesting. Okay,
yeah, we have it on the chat, right? So it's cstrack.eu. So that's the website, right? Mm-hmm. Okay, thank you, Miriam, for your presentation again.
Thank
you. Yeah, hopefully we can see your next phase of results in next year's CELDA conference. Thank you very much. Let's move on. We are a little bit ahead of time, but that doesn't really matter. We move to our third paper, which is exploring predicting performance of engineering students using deep learning. That's Imran, I assume, who will be presenting, right?
Yep.
Yeah, here we are. So the screen is yours, please.
Okay, let me see if I can share my slides. There you go. Can you see it?
Yes, thank you.
Okay, all right, great. Okay, I guess this morning or afternoon for us, morning for others. So my name is Imran. So I'll be talking about this exploratory study really in trying to predict performance of engineering students. I'm based at the American University of Sharjah. So I'm going to invite all of you to come to Expo 2020, which is happening right now. A lot of cool stuff there. So if you ever come this part of the world, please come and visit. All right, so here is the overview, the problem, a little bit about the previous work and what was the motivation for this work. Then we'll describe the data, the various prediction models we use, some results, and then conclusions and future work. So predicting student performance has been around forever, right? So this is sort of the classical problem. And people have looked at this for a long time. And why do you want to predict performance? Obviously, the primary reason is to detect detect dropouts, so you can take remedial action. Also, the other way around. Also, you may want to also detect people who are doing really well, and you want to put them in honors programs and so on and so forth. So there's a long history, and so I think there are many surveys on what has been done. And you can predict student performance meaning, let's say the GPA, to be very concrete, based on a variety of information, right? So digital platforms like MOOCs, etc., generate a lot of data. So I can use that. Many people have used that to predict performance if it's online. Student demographics, where they come from, for example, has also been used. Socioeconomic status, whether they come from a disadvantaged background or not, that information has been used as well. Clearly, gender is a part of it. One of the primary ones that has been used, which we'll use today, is prior academic performance, right? So if I know how you did well in the past, I can somehow use that to predict your future, right? So this is a fairly robust measure. Course load, how many courses are you taking? And by the way, this study is on tertiary education. And so obviously the factors will be different if you're looking at primary or secondary. Then there are other interesting things like, how do you perceive your relationship with the educational institution you are at? And so I could guess that using some instruments or surveys, and based on that, you can actually predict if the person is going to drop out, okay? Access to counseling, right? So do you have access to counseling or not? That also tends to be a determinant. And then there are many other psychological factors. People have designed instruments to actually figure out, based on an instrument, they can predict whether the person is likely to drop out or not. Now, what's going on here, right? So if you look at the type of data which is required for each one to make this prediction, this is fairly easy because it's already available. This is a little harder because you have to collect, a little harder, okay? This is very easy because typically most, this is talking about data, because most educational platforms already have, I have to give you a degree, so I need to keep track of your academic performance. This is also available readily, okay? These are not so easy, right? Because you need to actually go and collect these, and so this is sort of hard, right? Okay. And so you want to do something like this, for example, that means every student that came in, I'd have to have them do the survey, make sure it's valid, et cetera, et cetera. So it requires extra work, right? So if you look at, okay, so we use all that data and you say, how good are we at predicting, right, in general? And the input is varied, but I'm just going to give some general numbers, right? So if you look at some recent, I think there was a survey paper, if you applied machine learning, 38% of the current work was actually just predicting the final grade within a course, right? So basically you say, okay, I take a particular course, and can I predict what grade the student, so this is sort of at the micro level, at the course level. And then the next level is really at the exam, a particular exam or a test, right? So really think about it, I could predict, in a test, I could predict in a course, and the next level would be I could predict in a program, okay, and so on, right? So these are the different levels of prediction. So mostly the predictions are getting done at sort of, at least that's what the research showed, at this sort of lower level, right? Not that they're not done at the other levels at all. In terms of performance, how well we can do this, okay? You can go all the way up to 90 to 95, but in some cases, you're actually much lower, okay? So it's all over the place, right? Depending on which data is available. Generally speaking, if you look at traditional machine learning methods, and these are some of the well-known ones, these are, some, and I didn't put the actual papers here, you can look at my paper, but, SVM about 70 to 95, and 91, 85. So generally you're talking about approximately 75%, which is okay. It's not great, but it's okay. And that may well be because, that's really all I need. I just need a hint to see, hey, is this student going to survive or not, right? And then based on that, I can take some remedial action. Okay, so that's sort of where things stand. And again, this is using a variety of data, right? Not just one type of data. So our motivation for this work was, okay, because a lot of the data, like we talked about, like psychological tests or et cetera, is expensive to collect. What can we get away with? What's the minimum amount of data we could use, which is readily available, right? So we decided to explore if we only had prior performance data. Prior performance means GPAs in existing courses that they have taken, how far could we predict, right? And so this data, if you look at most universities, they actually do have this data. They maintain this data. They have to maintain it, and it's available. And you don't have to have additional privacy related issues, because then you have to ask people whether you can use this data or not. So we can readily use the data automatically every term to try to figure out what's going on. Okay. Most universities have departments that actually look at this, the issue of who's going to drop out, and they try to provide remedial services, so they can just use this data automatically. So the data that we used for this study, again, this is an exploratory study, was drawn from a registration system of one engineering program. This is important. If you want to look at structure, you have to be specific to a program, because the types of courses which will be taken within a program will be very different. Let's say if I was talking English literature. And so the pattern that you will see will be specific to a program. So here we are presenting the data on one engineering program. By that, what I mean, mechanical engineering, electrical engineering, and so on. This data was 4 years, from 2014 to 2019. So it's pre-COVID, which is good because COVID has caused all sorts of interesting anomalies, and we don't want to deal with that in the initial study. Now, the only courses which were in the engineering program were considered. Since this is an American curriculum, they have to take a lot of humanities and so on and so forth. And they were excluded primarily because we did not have access to those. We could have included them. And there's a large variability in those courses as well, because, as humanities, I have a wide choice of courses I can take. So that's probably add more noise. So that's the other reason we only considered courses which are taught only in the engineering programs. Now, the total students were 789, and they had registered a total of 10,508 individual courses over this time period. So, the average course is about 13.318 attempted per student. So the total courses, all the courses a student could take within this particular engineering program was 64. Okay. So that's sort of your maximum number of courses. So here we looked at 3 models, actually from the same class of models. These are neural network models, and they come from looking at sequence data. What we did not present in this paper, so I just put a note here, that we did try usual stuff like CNNs and 1D CNNs and some of the traditional machine learning, and it turns out they actually don't work very well. So then we said, let's look at these sequential models and see if we can get some better results. So let's get into it. So long-term, short-term memory networks have been around for a while, 10, 15 years. So basically, they take a sequence of size n, actually variable size input, and each sequence can have certain features. So in our case, we have terms. So terms meaning, the first term and the second term and the third term. And in each term, they can take a certain courses, right? A, B, and C. So this is our sequence, which is the sequence of terms, first semester, second semester, third semester. And the features are actually the GPAs in each course that they took. Okay, and obviously this will vary, right? So in the first term, one student may take, course A and course B, another student may take course C and course D, which is fine. But that can be incorporated in this technique. Okay. Now, obviously, if they did not take a course, so we just put a 0 there, or a very small number to indicate that, okay, in that term they only took courses with sort of the high GPA. So there's a little bit of issue with how do you handle if they got an F in the course, right? But turns out that actually it is handled. So the way we formulate the problem is, so let's say I've given you some students' performance in L terms. So let's say I say, okay, this student S1, I have the data on the first 3 terms, okay? But I want you to predict based on that, what will be their cumulative GPA in, let's say, the 5th term. This is important, right? So we're not just predicting the GPA in the next term, which is fairly easy, but you want to go, okay, the 5th term, right? Or the 7th term or the 10th term, right? I'm looking ahead almost a year, right? Okay. And what we did was we said, okay, let's, I'm really interested in 3 categories, right? So I'm going to have 1, 2, 3. So people who are sort of falling, these are the sort of at risk, whose GPA is below 2. And these are sort of the achievers, and these are sort of the mid guys, right? So sort of they're doing okay, they're not doing great. So the important point here is, given data from n terms, any number of terms, you can predict into the future any term, right? 5th term, 6th term, 10th term, whatever. And this is, I think, the interesting part, right? Because ideally what I like to be able to do is say, okay, a student came in, they are with me for 1 term, and based on that, I can predict where they will be 3 years from now, right? Obviously, that's very hard. But if I can predict even 3 terms, that's great, right? So that's sort of what we're shooting for. So if you think about it, again, just to be very clear, the input is, if you can think about it, each term is represented by this 64-dimensional vector. And let's say I took a course and my GPA was 3 and 2, and then 1 here. So these are all courses, right? So this is my input. And based on this input, I will predict, hey, what was your GPA, let's say, in the 5th term or the 7th term, right? So I'm predicting into the future, okay? So this is not obviously an easy task, right? This is, okay. So how do you generate data? Okay, and this is important, right? So basically what we're doing is we are going across students. So let's take 1 student, and this is 1 student who took many terms. And here is another student, and here's another student, and here's another student. So basically what I'm saying is I can take their first term, what they did, and go across students to predict, the next one. And then I can take the first 2 terms and so on and so forth. So basically we end up generating batches of data, which are used to train the LSTM, right? So the LSTM knows, 1 term, 2 term, 3 term, but we are going across students. And the reason this would work at all is because there is some structure in the program, right? You can't expect this to generalize if I was looking at English student versus, computer engineering. That's not going to work. But because they are in a structured program, they'll take similar courses. Now, in terms of number of batches that were used to train, so basically, this gives you an idea of the student set that we have, how many terms they had completed, right? So 480 had only completed 1 term, right? And then 455 have completed 2, and so on, right? So basically, this data, this 455 one, I can only use to predict, from 1st term to the 2nd term, and so on, right? So there are limitations on how much data you have, and this is one of the problems, right? Because even with 5 years of data, you can see that when I start going towards people who are near completion, the data is lesser and lesser, obviously, because it's a moving window, right? Okay. So here's an example data. So I'm showing you 4 students. So this data is for 15 terms. So you can see that the terms are going this way. And then this is each course, right? The GPA in each course. Okay. So it becomes a picture, right, in a way. And this is their cumulative GPA at the end of the here, right, at the 15th course. So you can see this student is really smart, right? Their GPA is 3.9. And you can see the pattern, right? You can see that they're all whites, meaning they did well in those courses. So what we're trying to do is we're trying to take this window here, right? So if I say, I'm going to give you data on 5 terms, you try to predict the GPA, right? So in this case, the window for this person will be this, right? So this is a window for somebody doing so well. And this is a window for somebody who's doing, sorry if I draw this correctly, and so on, right? And this is a window for somebody who's doing real well, right? So basically, the LSTM is getting trained to say, okay, look at these 4 windows, basically, which are sequences. The sequence is important, right? Like this. And then try to predict the GPA, okay? So this is just for 15, and we do that for any number of terms. It's completely general, right? And here, this is 64 here, because they can, in this particular program, they can take a maximum of 64, right? So this is a nice visual representation. And again, we tried CNN, it was kind of cool. It worked too well, but it gave us some results, and turns out that LSTM is better, okay? So how do we train these models? So that's our data, right? So we took all the data, kind of converted it into that format. So we use a very typical, neural network approach of 80-20 split for training versus testing. And then within the training, we did a 70-30 just to check for overfitting. We did hyperparameter optimization, came up with a couple level of stack models and so on. Details are all here. So an important thing is that we use generators to dynamically generate the data that you saw, and then the systems were trained on it. So let's look at the results. So what you see here are 3 metrics, and I think accuracy we are most familiar with, so I'll talk about accuracy. Actually, the more accurate measure is F-score, which is the geometric ratio of precision and recall, but let's talk about accuracy. So what you see here is for LSTM, which is the first type of model, and this is the number of terms you are predicting ahead. So this is the model. So these are actually 17 models, right? 17 models. So this model is trained only to predict a single term ahead, right? And this model is trained to 2 terms and 3 terms and 4 terms and so on, okay? And you can see that if I kind of plot the, something like this, right? So this is my accuracy, right? So it's kind of around the same ballpark, 70% or so. And then it drops down, but to 40, which is not great, but that's almost like guessing. But remember, there are 3 parameters, but I'm doing pretty good here, right? In this, I can predict up to like 4 or 5 terms, right? Okay, so that's LSTM. Now, one of the things we wanted to see was, hey, is this model overfit? Because we have millions of parameters here. And you can see, and these are sort of learning curves. So you can see that no overfitting, no overfitting, no overfitting, no overfitting, really no overfitting, but here clearly there is overfitting, right? So you really reach the limit, right? You're trying to predict 16 ahead, right? And so what happened is the amount of data available is also much less. So you expect this to happen. But remarkably, all the way going up to 14 with this very small of data, really you don't see a lot of overfitting, which actually is kind of interesting. Now we can see similar results for GRU. And GRU is, again, a modern form of LSTM. It requires less number of parameters, but the results look very similar. Again, it's a slightly better, actually. So if you look at, for example, the accuracy, it's about 70x%, but you kind of see the same effect as expected. Okay, and again, here you're kind of okay, and then as you start to predict farther down, things don't look so great. Right? Now, interestingly, if you look at sort of the overfitting side, it's doing much better because it has less number of parameters than LSTM, right? So generally speaking, it's not overfitting, but even for predicting for 16 terms, it's doing okay. It's kind of interesting, especially because you have such a small amount of data at those levels. Because remember, to train it for predict n equals 16, I really have to only look at students who are almost about to graduate, right? Which is a very small number. It's like, I don't know, in 100, not even 100, right? So that's very interesting, actually. And they tell you that there is a structure, right? Obviously, if there's no structure, you would never see this type of performance. And then bidirectional LSTM actually looks at data going forward and backwards. It actually did slightly better, but not really, right? So it's similar again, similar behavior. But if you look at overfitting, it looks more like an LSTM. So really GRU would be so you can see it's kind of falling apart here, right? So this is not good. So GRU would probably be the model to go with if you look at just these three models which are looking at sequencing. Obviously, I have not presented the other models, so I cannot give you the data on that, but just for these three. Now, generally speaking, I guess the point is that predicting forward, based only on performance data, we can do kind of okay, right? So the F1 score, which is the sort of combines both accuracy and recall, if I say, okay, I'm willing to live with about 0.7, and by the way, 0.7 is kind of similar to like human sort of judgment type stuff, right? So I'm okay until, regardless of which model I use, I'm kind of okay until predicting until 5, right? And then it begins to drastically fall here, regardless of the technique. So this is really embedded in the data, right? So the data, with this particular data, regardless of the technique, I can predict forward. Now, if you think about it, 5 terms, meaning that if a student came in the first semester, and then you're telling me, hey, how is he going to perform in the 6th semester, right? So that's looking ahead a lot, right? So I think this is a lot of information that you're getting. And remember, it's not just the first term. I can ask you in the 3rd term how they will perform in the 9th term and so on, right? So it's not just starting from the beginning. So it looks promising, right? That's my point, right? And this is expected, right? There's just not enough data there for me to be able to do that. Okay, so the conclusions, really, I think I'll talk, there's too much text here, mostly about 2 things, right? So one is, as I said, we tried traditional machine learning. SVM generally has done well. It'd be interesting to just do a formal analysis just to see how well it works. One problem with traditional machine learning approaches is that very few of them allow variable length data, right? So the LSTM, we are training it on, 2 semesters, 3 semesters, 4 semesters, 5 semesters, 7 semesters, and that'll be difficult to model in most of the traditional techniques. So, but it's doable. The key problem is this actually, which is the lack of data, right? We have enough data. We have fairly good engineering schools. So in one program, we only have 800 students, right? Only 10,000 courses. So you need to use something like a GAN-based approach. And there's at least one paper that has actually done this in a similar context. And I think that's really the future work, is to actually say, okay, maybe we had to use a GAN to generate synthetic data. And then we can actually improve the performance further, because the data, regardless of, unless you have a very large engineering school, you're going to be limited in terms of data, right? So I think that's the way to go in terms of actually pushing the performance even further. Okay. And I guess that's it. That's the end of my talk. That's my email. And I'm very happy to take any questions.
Thank you very much, Imran. This was very data heavy, but absolutely great insights we have from you, and great explanations you did in your presentation. So are there any questions coming out of the audience for Imran? I think many educators would like to, build interventions based on what you have been doing and presenting here. So are you planning to also use your data sets and your analysis approach to really build interventions and
yes,
make this available to educators?
Yeah. So basically, look, I mean, the key thing is these models are context specific, right? So right now I have engineering data from all the programs, right? So I've only shown one engineering program, but I can tell you that the performance is similar across engineering disciplines, industrial and so on and so forth. Yeah. So one of the plans is to actually, because this data can come directly from a registration system, it's fairly easy to write a service which will automatically generate this data and give it back. So yeah, so we have plans, and we have in our university, and most universities do, we have a whole sort of department that actually looks at exactly this, to identify. So the idea is to, okay, we're going to take the data, automatically extract the data from Banner, which is our registration system, and run this analysis and give this to this particular department, which deals with exactly this issue. And then we'll evaluate to see, okay, did it have an impact or not, right? It's difficult to tell, right? Right now, just whether it'll have an impact or what type of impact. Yes. And the nice thing, as I said, is I don't need to do anything, right? I don't need to collect any new data. I just grab the data from which is already there and feed it into the models and provide it to the concerned people, right, who deal with this.
I fully agree on this side, and I like your approach. Providing the information to the educators or to the decision makers in the departments, and then they could provide any actions towards the programs or towards specific lectures, etc. That's exactly the same approach we are doing at Curtin University in Australia, where we also use a centralized system and building a centralized insight from our algorithms, and then moving it into the departments. And then they are, of course, on actions and doing whatever they want as an intervention. So that's exactly, I think, which is the right approach. But on the other side, we also had always discussions on ethics around the data. And,
yes.
And is there anything you also include in your decision-making process? Because I think you lightly touched also the fragmentation of data, which is of course an issue. So wrongly predicting, student outcomes is always, of course, an ethical point of concern. And how did you approach this?
Okay,
and also looking at the student's perspective, what are student perceptions towards that end?
Okay, so we are very much concerned about the ethics of this. So one of the reasons actually we want to restrict ourselves to the GPA data only is because the students have already agreed to make this available to the university. So that's one, right? Obviously, it's anonymized. We do not identify individual students. And then secondly, there is a process in the university which is already in place where a particular program only, which means there is in the case of, let's say, a program like computer engineering, only the head has access, right? So they already have the rights to access this data. And then there are particular departments within the universities, just one, right, which is already has the rights to access the data, and that's it. So nobody else will see the data, and the data will only go to people who already have passed sort of the ethical, bar to see, okay, you must have this data, otherwise you cannot do your job, right? And yes, the students have to agree to it, and they currently do agree to sharing just that data. So yes, and this is, again, one of the reasons why I'm not very keen on, okay, let's do a psychological survey and so on. They're interesting, but then again, all these issues start popping up, right? So that's one. Now, in terms of the silos that you create. So for example, if I go to the registrar in our university, who's the keeper of all this data, they will only give me data pertaining to engineering, because that's the data silos, which is protected. They will not give me data pertaining to English or humanities or math, which is fine. I think that's okay. In this particular approach, we did not have that data because we did not have access to it. But in my opinion, even if we did have access to it, it's probably going to add noise because there's too much variability in that data, right? So we just got lucky on that. But in general, your question is very valid. Let's say I'm concerned about how my engineering students are doing in communication courses. Then I have to go through the proper channel to request the data, right? And it gets very messy actually, right? Because there are political issues. People do not like to share their data. So I think in our case, if you stay within a school, like a business school or college of engineering, and there is a buy-in from the top management, which obviously I had to get, that problem is somewhat resolved. But going across the university, I think it'll be very difficult. Now, most universities, as you know, do have what are called institutional effectiveness departments, and they have data from all programs. So they do have data from across the university. So they could do something like this, but I think politically it'd be very difficult. I mean, it's not so much an ethical issue. We always have the ethical bars in place, but it'll more be of a political issue. Yeah.
I fully agree, and as I said, we have this centralized approach at Curtin University, but we still have our context around the data as well, meaning that that we don't mix the data from different subject areas, for example, because that is a really a big danger in decentralized entities of organizations, that they mix up all this contextual idiosyncrasies. And we've done a study with 1 million enrolled students a few years ago, and that showed clearly that there's, of course, significant differences between different departments or between different domains in terms of predictive power of the algorithms. So if you use the same algorithm and not the context-based algorithm, that might have big limitations, of course. So I really appreciate your approach here and saying, okay, this needs to be part of a department or part of an engineering group or language group or things like that. So that's very important, and that's what I see as a big danger, to mix up data silos and yeah.
I mean,
validity in the predictions.
Yeah, I mean, one of the things we did not consider here, by the way, and this is interesting, is the dependencies, right? So what we find, for example, is there are dependencies, right, across. For example, if they did not do better, if they don't do good in calculus, you know they will fail in mechanical engineering, right? But unfortunately, like you said, we just don't, we don't mix it up, right? We convey that information. We have channels to convey that information to the appropriate programs, but I think the data will never be shared, just for political reasons.
Yeah, absolutely agree. Are there any other comments out of the audience? We have a few more minutes left. If you have any questions to Imran for this interesting project. Seems not to be the case. So again, thank you very much for your presentation. That I think we learned a lot about your data and your approach. And hopefully we can see you back next year at CELDA for maybe getting more insights into this project.
Definitely, I look forward to it. Thank you.
Thank you. So let's move into our last paper for this session. It's titled Evaluating Visualizations for Slide-Based Investigative Learning with Connection Between Presentation Slides. It's Mitsurio already being visible with the Golden Gate Bridge behind us. So you could start and share your slide if you like. We cannot hear you. We see your slide, but we cannot hear you. Can you try to reconnect your audio? Because there's no audio coming through. Oh yes, now we can. Yeah.
Mm-hmm. Yeah. Okay. Thank you. Let's start my presentation. Okay. Thank you, Chair, for your introduction. Good morning, everyone. I'm Mitsuhiro Goto. I'm a student at the University of Electrical Communication in Japan. Today, I'd like to talk about evaluating visualization for slide-based investigative learning with connection between presentation slides. Okay, at the beginning, I'll show you the overview of my presentation. I propose a slide investigator spot with a visualization structure of presentation document during slide-based investigative learning. And our key idea is to visualize the roles and the logical connection between the slide in P document. I also report the result of a case study with 16 participants. As a result, the proposed visualization was effective for slide investigation. This slide shows the contents of my talk consists of 4 points. Okay, let's start First and second point. And the number of the presentation document to be shared is increasing rapidly. For example, we can use well-known web services SlideShare having 14,000 documents related to deep learning now. There are various kinds of presentation documents to be shared on the web, which are created for academic conference, survey reports, and technical seminars. This presentation document represents the contents appropriately and precisely. In response to this trend, I noticed that learning resources used for investigative learning have been changing. Investigative learning is one of learning styles. Learner explores the learner resource to learn with their own learning goal in self-directed way. The learner used to learn with book or web resources recently has been increasing opportunity to utilize presentation document as a learning resources via the web services such as SlideShare. We call this investigative learning with presentation document SBI learning. We have been designing the learning support for SBI learnings. This is a model of SBI learning. This model including 3 phases like this, which are repeated until the investigative learning process is completed. I'll explain the overview of a model with an example where a learner is expected to learn about deep learning. First, the learner is expected to explore the P document about deep learning and select a P document. Then learner is expected to investigate slide to be learned from the document. In this phase, learner is allowed to identify the segment of the document, such as model, system, evaluation, etc., and to select the sum slide. Next, the learner learns the contents of selected slides. In this phase, the learner is allowed to extract and integrate keywords representing learning, learned, and knowledge, and compose a keyword map like this. In this example, learner finds out the keyword object recognition from the map to investigate the P document. In this way, if the learner finds out the keyword out to be further investigated in the map, learner is allowed to repeatedly conduct these 3 phases investigate. See like this. Okay, next, I'd like to talk about detail of phase of slide investigation. I think this phase is the most important in the model because learner will finish learning with incompleted knowledge in subsequent phases if they cannot find the slide to be learned. Today, let me focus on how to resolve the problem in this phase. The roles and connection of slide tend to implicitly expressed in presentation document. In order to investigate slides in P document for learning, learners need to grasp the contents all of slide to identify the segment. By the way, P document can be divided several semantic segments that embody the main topic of presentation, such as sub-themes or topics. Each segment also contains a series 1 or more slides, which are logically connected to each other. The learners also need to comprehend the connection of segment or slide. These processes allow the learner to find out the slide to be learned using structure of P document. However, it is very complicated and difficult for learners to identify the role and the connection of slide. In order to resolve the problem I just mentioned, we have proposed a visualization enables the learner to understand the structure of P document. In particular, we focus on how to identify the segment or slides. Our approach is to provide the learner with a visualization map that helps the runner to grasp the roles and the logical connection of slide in a shorter time. We call visualization map slide map. Okay, next, I'll talk about slide investigation support. This slide shows the overview of the slide map. The slide map visualizes the structure of P document with the rows and logical connections of the slides. This map consists of 3 areas, which are main sequence area, support sequence area, and rebuttal sequence area. Also, each slide is represented as node like this, and the connection between slides is represented as a link between the corresponding node like this. In main sequence area, the slide describes the main topic transfer to audience. In support sequence area, the slide provides content supporting slide in the main sequence area. This slide support this. And in rebuttal sequence area, the slide provides the content rebutting the slide in the main sequence area. I'll explain how to use slide map. For example, runner runs the main topic by pushing the slide sequence in main sequence area. And this slide helps the runner promote their understanding of the slide in the main sequence area. Okay. In order to represent the logical connection between adjacent slides, this study adopts the function of conjunctions. In this study, we follow the function of conjunction in Japanese, which are classified by Ishiguro. He defined 10 types of conjunction connection. This table shows these types of conjunction connection. Connection without function of conjunction is defined as simple connection. This connection type allows the runner to comprehend the structure embedded in a presentation document in a short time. Okay. This slide shows the link type, which are visualized from the source slide from source slide to destination slide in the map. According to the connection type, link types are link to support sequence, link to rebuttal sequence, link to main sequence, and link to same sequence. Such visualization helps the runner readily grasp the structure embedded in the document. This slide, an overview of the visualization tool. We have developed a visualization tool for slide investigation, which is implemented as an add-on for PowerPoint. This tool has 2 display areas. One is for slide map, shown on the left. The other is for slide in detail, shown on the right. I'd explain a framework of the proposed tool. Firstly, when the runner inputs P document and corresponding definition file to the tool displays the map and slides. Secondly, operating display map by mouse clicking or keyboard, runner can obtain information to identify the segment or slide, and they can find out the slide to be run. In next slide, I'll show this function in detail. First, the tool loads the slide map definition file to automatically calculate the position of each thumbnail and generate this slide map. Currently, this file is generated manually, and definition file consists of slide ID, link source, connection type, slide type, to be writing. Okay. And next, the slide allows the runner to check the slide information such as slide ID and slide title. In Japanese. Okay. And the magnified thumbnail image by hovering mouse over like this. Use the mouse over the thumbnail and magnified image displayed. This function helps the runner grasp the contents of each slide quickly. Next, the tool allows the runner to change and switch the display by using arrow key or clicking slide thumbnail in the slide map. This function allows the runner to access the slide they want to view quickly. Okay. As for how to generate the slide map, we are now investigating the possibility of generating the slide map automatically using conjunction in oral explanation. Yeah, our key idea is extracting the conjunction from not only the contents of the slide, but also the note area of PowerPoint and audio data of the recorded presentations. These texts tend to use more conjunction than in slide. Now, let's move on to the case study with the proposed tool. I conducted a case study with 16 participants to verify whether the proposed tool was effective in slide investigative phase of SBI learnings. The participants were 16 undergraduate and graduate students of information engineering, 12 males and 4 females. The participants were required to investigate and run slides using 2 UIs. One is PowerPoint, the other was slide map UI. I conducted within participant design and require each participant to use each UI. The evaluation metrics were running time, understanding test, usability questionnaire, and subjective questionnaire. The P document used in this case study were 2 documents obtained from the slide shared. One was a document of renewable energy called Doc1. The other was a document on zoology called Doc2. These documents have the same number of slides, the same number of segments. Average number of slides in a segment is almost the same, and prior knowledge of participant is almost the same. 2 conditions were set. One was for running Doc1 with PowerPoint UI, we called PPT cont, and the other was for running Doc2 with slide map UI called SM cont. And we prepare viewpoint for running. We also set 2 viewpoint per 1 document. For Doc1, V11 and V12 set, and for Doc2, V21 and V22 are set. This slide shows the procedure. Each participant was required to do 2 sessions under 1 condition and to do total 4 sessions in this case study. The participants were instructed to investigate the slide related to the viewpoint provided and to understand the detail of slides. The running time was within 20 minutes in 1 session. If participants finish running earlier than 20 minutes, participants were also required to tell the experimenter. After 1 session, understanding test, usability questionnaire, subject questionnaire were required to answer. Okay, now I'd like to talk about the result of case study. This graph shows the result of running time and understanding test. First, let's look at left graph. In first session, the average time in SM cont was about 1 minute shorter than PPT cont. In second session, the average running time in SM cont was about half of the average time in PPT cont, like this. And the understanding test consists of 5 questions about the contents of slide, each of which was given 1 point for a total of 5 points. When a question was answered when a question was answered with multiple elements, the second was the square was divided by 1. Next, look at the right graph. Square is SM count higher than PPT count for session, like this. In first session, there are significant difference, and in second session, there was a tendency of significant difference. This result suggests that the slide map encourages the learner to investigate the slide related to viewpoint in a shorter time than PowerPoint. Okay, I show the result of focus on the slide related to viewpoint. Left graph shows the ratio of learning time. Right graph shows the ratio of viewing frequency. The ratio represents the number of the viewed slide related to viewpoint divided by number of all of the view slide. If this ratio is higher, it suggests that the participants spent more time or view more frequency for learning slide related to viewpoint. Okay, first, let's look at left graph. Ratio of learning time in SM count were higher than PPT count in both sessions, especially in second session. The ratio of learning time in SM count was 30% higher than PPT count. Left graph shows SM count helps the participant to focus on the learning the slide related to viewpoint than PPT count. Next, look at right graph. Ratio of viewpoint frequency in SM count was almost the same as the ratio of ePPT count in first session, and higher than PPT count in second session. Right graph shows that SM count helps the participant to revisit for learning the slide related to viewpoint than PPT count. This result suggests that the slide map you are encouraged learners to more intensively investigate the slide that are suitable for understanding than PPT, the PowerPoint. Okay. I'll next show the result of questionnaire. I conducted 2 type questionnaire from the participant. One was system usability scale, SUS, shown on the left graph. Participants were required to answer 10 questions of SUS. If the SUS score is closer to 100, it indicates a higher usability. As you can see, SUS score of SM count were higher than PPT count. The other was subject to questionnaire with 5 Likert scales shown on the right graph. It includes a 4 question item from Q1 to Q4, like this. All items of SM count were higher than PPT count. The result suggests that the slide map UI had higher usability for investigation the slide than PowerPoint. From the above the result, I conclude that a slide map is more effective for slide investigation than PowerPoint. In conclusion, we've designed a model of slide-based investigative learning and designed a slide map which visualizes the presentation document structure for grasping the roles and the logical connection of slide. And we've also reported an evaluation of effectiveness for slide investigation with slide map. In future work, we need to address these 2 points. We will use the function of automatically generating slide map and function of authoring the slide map definition files. And we will study the learning support for other phases in SBI learning. We studied a phase of knowledge building based on keyword map and a phase of investigating as a P document from the web. Okay, that's all my presentation. Thank you for your attention.
Thank you, Mitsuhiro. This was a very practical insight you provided us on your project.
Yeah.
Are there any questions towards this presentation? or comments? So looking at your tool, I think it has lots of values, and of course, you know, as you said in the beginning of your presentation, there's so many different presentations available, and students can make lots of use of these presentations for their own learning and self-regulated and self-directed learning. How easy or how long does it take to transfer, you know, slides into slide map? What is the time you are taking? Because you said, you know, as an Outlook, you want to automate all this stuff, but how long does it take at the moment to make it available?
Sorry, how long does it take?
Yeah, what is the time scope? I have, so, you know, I'm having now a slide deck available, and I want to use your slide map for learning purposes. So what is the time frame I can, you know, transfer the slides into your system?
Our current system is not automatically generate slide map.
Yes, right.
And,
yeah.
And we prepare the definition file for a slide map, and the system loads to generate a quick map, and runner can use map and for running. So and
So will you build an interface?
One more question.
Yeah. So will you build an interface for teachers in the future to automate all this, or where I just upload a, you know, a slide deck and I have then the system available, or how do you envision this will look like? So what would be the automating process in the future?
Yeah. We will investigating the possibility of automation, and sorry.
Can everybody use it then, or is it a limited system at the moment? Could I use it, for example, as well, the system at the moment, or is it too is it only in Japanese, or is it also available in English or in other languages?
Now our system used to only in Japanese, but text. Sorry, I think we use text mining technique, and sorry, in Node-RED PowerPoint text. Yeah, I think sorry, how to say maybe our system available in English because we utilize text mining technique and extract the conjunction from slide text, not radio, and audio data converting text.
Yeah. Okay, yeah, I think that this would be valuable, you know, to have the system really available in other languages as well, maybe English and whatever language you might choose, and the text mining technique would be a great approach to have been presented next year at CELDA, I believe. You come back and present your text mining and automation process of SlideMap, because I think it's very valuable what you're presenting. So thank you very much, Mitsuhiro, again for your presentation.
Yeah.
This is a great work. We want to follow up later on. So this concludes our session today, the first morning session for CELDA. We have a short break coming up now, and then we continue at 11 Portugal time with the last session before we move into our closing session. So please stay tuned for these two remaining sessions. At the closing session, we're going to look into the best papers, of course, and also look into next year's edition of the CELDA conference, and of course also the present the publication opportunities coming up from this year's CELDA conference. So stay tuned for these remaining two sessions. We have a 50-minute or 20-minute break now, and yeah, come back to this room later on. Okay, thank you very much for all the presenters today, and see you soon.
Thank you. Bye. Thank you.
Thank you.